Welcome back to HackCode. In this video, we're tackling an essential problem for coding interviews, word break from LeetCode. This problem is great for learning dynamic programming and recursive problem solving. We'll explore three approaches: brute force with recursion, recursive with memoization, and dynamic programming bottom-up, that is tabulation. Let's break down the problem step by step and understand how the solutions work. So sit back, relax, and let's dive in. Before we dive in, I want you to be aware that this question is most frequently asked in top product companies like Adobe, Amazon, Apple, Bloomberg, Facebook, Google, Microsoft, Oracle, Snapshot, Twilio, Uber, VMware, Walmart Labs, etc. So be sure to solve this problem. So now let's dive into the problem statement. Given a string S and a dictionary of strings, word dict, written true if S can be segmented into a space-separated sequence of one or more dictionary words. So basically all we need to do is we need to split this given string into a space-separated words. That means like we had to split this string and put a space between these two characters. So here if we put a space, we get lead and code. So that's what we have in example one, wherein we have string S given and the word dict. So word dict consists of the two words LeetCode. Okay, the output is true because we can split this string into the words in the given dictionary. Okay, they also given that note that same word in dictionary may be reused multiple times in the segmentation. So basically we can reuse the words in the dictionary. Okay, so let's look at example 2 which will clarify this. So we have apple, pen, apple here if we split this, and in word dict we have apple and pen. So in this case also we can return true because we can reuse this word apple, right? So if we split here, it is what apple, pen, and apple. So we can reuse this apple twice and pen once. Okay, so here output is true. So this is the same expression they're given, return true because apple, pen, apple can be segmented as apple, pen, apple. Note that you're allowed to reuse the dictionary word. Okay, so now let's look into example 3. This would give you more idea on the failure cases. So here we have string is given as cats and dogs. So at each time we split it, we can form only two words from the dictionary. You see, right? So here if we split at cat, we can form either sand or dog. So out of all these words, we are able to form two words only, which is cat and one of this sand or dog. So if we choose to go with dog, we can't form sand. Okay, similarly, if we choose to go with sand, we can't form dogs. So only two of the given three words are formed. So in other ways as well, so if we split at cats, we have the only possibility is dog. Okay, basically we are forming only 2 out of 5 words in the given dictionary. So that's why we had output false, because we not able to split this string into the all the words in the dictionary. Okay, so what are the constraints here? S length in the inclusion range of 1 to 300, and the word dict, so basically this dictionary list length is in the inclusion range of 1 to 1000, and word dict of I.10. So basically the words in the dictionary are in the length of 1 to 20. So what should we learn from this? So basically while forming the solution, we should be knowing that we can perform only 10 power 8 operations per second. If we exceed this, we'll be getting the time limit exceeded. So this is the hard limit of the complexity we have. Okay, so we should fit our solution with a 10 power 8 operations per second. Okay, so that's the idea, guys. This is what we should get from the constraints. And next, we have S and word. It consists of only lowercase English letters. This is not that much critical. This is just like they're saying that it consists only English letters. And next is word. All strings of word dict are unique. So basically, they're saying that all the strings are unique. So we don't need to care about duplicates. It consists only unique words. Okay. This is the boilerplate code given, wherein we have a word break method which takes the string S and the word dict, which is a list of strings, and it returns a boolean. So this boolean represents what? This boolean represents if we can segment the given string into a space separated sequence of one or more dictionary words. So now let's go to approaches. Before we get started, I want to remind you about our exclusive blind spot info post. This carefully curated collection covers essential coding interview problems to help you master the most common patterns and excel in your interviews. Whether you're prepping for FAANG level interviews or just sharpening your problem solving skills, these problems will ensure you're ready for anything. Even if the exact questions aren't asked, they cover all the important patterns. So be sure to check out our playlist and stay ahead of the competition. So firstly, let's go to the recursive solution. This is basically a brute force approach here. Okay, so what's the intuition here? In the brute force approach, we try to segment the string in every possible way. For each prefix of the string, we check if it exists in the word dictionary. If it does, we recursively try to solve the problem for remaining part of the string. This approach expresses all possible combinations without any optimizations. So basically here, what we are doing, we're trying to segment the string in every possible way. So, and what is a prefix here? So prefix is basically, this just starts at the given, start of the given string, and it can end till like at whatever point till the string ends. So that means if you take the LeetCode, so this is the given string. For this, empty string can also be the prefix, and then L can be the prefix, and LE can be the prefix. So on, we can take till what? Leet COD. So this can be a prefix. Next is LeetCode. So basically, the whole string itself can be a prefix. So this is just like we are considering from the empty string to the full string. So this we can also say as substring. So substring also be like, it can start from the empty string and can till go until what, LeetCode. Okay, it could be part of this string. So like if we take this etco, this also is substring, and code this also substring, likewise. Okay, so firstly what we trying to do, we just take a prefix of this particular string. That means like we can take till leet. Okay, and then we check if it exists in dictionary. So here a leet exists in the dictionary. So next what we do, we try to solve the problem for the remaining part. So basically for the remaining part, we need to see if it also exists in the dictionary. So when we sit at leet, we can just check for the code, right? So that's what we're doing. So this part of the string also requires the same check as of leet, right? So that's why we do a recursive call. That's the idea, guys. Very simple. Okay, it's just that we need to think of the problem statement and we have to just formulate the solution based on the problem. Okay, so what is the algorithm? Convert the word dictionary to set for the faster lookup. So why is this required? So basically we should be aware that the lookup in the list takes O of n time. Okay, O of n, because it has to scan through all those elements in the list to get the idea of if the particular word exists in this list. Okay, but for the set, it is all indexed. That means that it is a hash based set. So if you put in a set, then it would be just like O of 1. So it can directly say if this word exists. Okay, that's why we had to do this for the optimization. Okay, so in step 2, define a helper function that starts at an index and tries to check all possible prefixes. So basically we discussed here, right? So we'll start at one index, let's say I is equals to 0, and then we have to express for all possible prefixes. Prefixes are nothing but what we discussed, right? Like it can go till end of the string, but it starts at the start of the string. And also empty string can be a prefix as well. Okay, in step 3, if the prefix exists in the dictionary, recursively check for the remaining string. So we discussed, right? So if this prefix exists in the dictionary, we have to check for the code. Okay, so if both are exist in the dictionary, then we can return true. That's what the step 4 is about. Return true if all parts can be segmented, else false. So basically if all parts can be segmented, we have to return true. Else, like if only one part is segmented, we have to return false. That's the idea. So that's to create the code. So it's just a translation of algorithm we have. So firstly what we are doing, we convert the word into set for the faster lookup. So that's why we're doing word set, like we define a variable, we're doing set of word dict. So basically this is converting the list into set. Okay, this is for the faster lookups. This would be O of 1 lookup. And step 2, define a helper function for recursion. So this is the recursive helper function we have. This takes the index. So the index is where we start looking at. Okay, so what is the base case here? So always a recursive function should have a base cases, else it would keep on calling itself and would get recursion depth exceeded. So that's why we should have base cases to have it stop somewhere. Okay, so here the base case is if we reach the end of the string, we return true. Basically if you are able to reach the end of the string, that means that we explode till the end and we were able to split it into words. Okay, in that case only we explore, and that's why we had to return true, because we reach till the maximum possible index. So maximum possible index is what? Length of string minus 1. So if we reach till length of this string, that means that we exceeded the maximum possible index. So we had to return true, because we were able to traverse the string, and we traverse the string only if we are able to break the string into the given words in the dictionary. Okay, step 3, iterate all possible substrings starting from the index. So index is what we're getting for the current recursion. So it starts at 0 for the first time. Okay, from 0 we have to explore till the length of the string. So only when we explore till the length of the string, we will be able to form the overall string, right? So that's why. So here in this case we are considering the end from the index plus 1 till length plus 1, because this length plus 1 is what the exclusion, right? So it will generate only till length, and this length also here it would be in the exclusion range, because here we're considering the slicing. In slicing as well, this is exclusive. So here we're considering only till the valid index, which is length of string minus 1. Till this point only we'll be slicing the string. So here initially we would be having a 0, right? So from 0 till length of the string minus 1, we would be getting what? The entire string. Okay, so that's what the idea, guys. So here we are doing length of s plus 1 because we have it covered here. You won't be getting index or the bound exception. Okay, and here if this is in word set, we will explore the further half. So that means like we have sliced it till here, then we can explore the other half. That's the idea, right? So that's how we're doing that. Okay, and then in this case we can return true, because if helper of n as well returns true, then it means the word code is also in the word dict, right? In that case we return true, because this also return true and this is also true. So that's why it is true, guys. Okay, another case where we explored all possible substrings and still couldn't be able to split this, then we had to return false, because no valid segmentation found. That's why. So this is for that case. So here this is the definition of a helper function. We just call the recursion from the index 0. That's why we return helper of 0, which calls the recursion from the index 0. So from index 0, we explore all possible substrings, okay? So let's look into complexities. The time complexity is of 2 power n, where n is the length of the string s. This is because at each string we have two choices, either to include the current substring in our segmentation, if valid, or skip it. So we have two decisions to make. So that's why it's 2 power n, because at each index it is two decisions. So particular I, it is two decisions, either to include or exclude. So this is two decisions. And how many such indexes we have? That is n indices, because we have the string of length n. So this is what 2 power I. So here I is replaced with n. That's all. Okay. The space complexity is often this is for the recursion stack. So basically recursion stack, it is maximum it will be at what, n length. That's why it's often after n length it would start processing and it would be popping up and processing the further stacks. I got the code ready here. Let me try running this. So this active solution for the three cases. Let me try something this. Time limit is exceeded and only 35 out of 47 test cases passed. This is because our solution is having exponential time complexity and it won't be scaled for the larger input string. So that's why we have to optimize this. So let's look into further optimizations. So let's look into recursion stack, which would help us to identify the bottlenecks in the current approach. So for this, I'm considering the given example, which is cat and dog. So for this, we have a word it as cat, dogs, and cat. So here, going by the recursive function definition, we have helper of index. So I represented helper of index here. This index could vary from 0 to length of s minus 1. So here, length of s is what? It is 9. So the most valid index is 8. So the index varies from 0 to 8 here, okay? And next is, we make a recursive call only if this s of index till n is in the word set, okay? So basically this is the exclusive range we should keep in mind. So let's consider the first iteration here. Our n would be at index plus 1, which is n1, okay? And now we'll be slicing till 0 to 1. So this 1 is exclusive range. So at 0 we have C. So we would be getting only what? C. Okay, and C is not in the wording. That's why we don't make a recursive call and n would be incremented. Now n would be at what? It would be at 2. Okay, so now what we will be getting CA, but CA is not there in the wording. So that's why we just continue. Now n would be incremented and it would be at 3. So now the C8 is there in the wording. So now what we do, we make a recursive call by helper of n. So n would be at 3, right? So we make a recursive call for helper of 3. And next, similarly, we have cats in verdict, right? So we make a recursive call with what? Helper of 4. Likewise, we have all these calls, okay? Now let's take a deeper look. So here, if we consider this recursive stack, we are seeing that there's two redundant calls made for helper of 6. So no matter how many times we call this helper of 6, the value written by that is same, right? And also here helper of 10 is called for twice. And similarly helper of 7 is called for twice. So basically here there are a lot of redundant computations happening. Due to these redundant computations, we are losing the time. So that is leading to the increased time complexity here. So what if we save these results once we compute, and next time if we encounter the same subproblem, we can reuse the result. So that's the idea, guys. I'm talking about the dynamic programming top-down approach. So here once we encounter a subproblem, we solve that and we store the result, okay? And next, if we encounter the same subproblem again, we use the compute and store result instead of computing the subproblem again. So basically it would help us to save a lot of time, and hence it would improve the time complexity, okay? So this is a brief about how we're going to solve this using the top-down dynamic programming approach. So now let's look at the top-down dynamic programming approach, which is memoization. So here the time complexity would be reduced to O of n square. So what is the intuition here? To optimize the brute force approach, we use the memoization to store the results of previously computed indices. This avoids redundant computations and significantly reduces the time complexity. So it makes sense, right? So basically once we compute the subproblem, we store it, and next time we use the stored result instead of computing again. That way we are saving our time. So just a heads up, in later point of the video, I'll show you how to convert this brute force with recursion to the memoized version with just a one line change, okay? But to understand that, you need to be well versed with this algorithm, okay? So then only you could be able to understand that. So now let's look into the algorithm. So step 1, we create a dictionary to memoize the results for the each index. So basically we require some storage, right? For that storage, we're using the dictionary. That would help us to do lookups in O of 1 time, okay? For that dictionary, what is the key here? Each index is the key, okay? So the key would be each index. Keep in mind, okay? And next is step 2. Define a helper function that starts at an index and checks all possible prefixes. So basically this is same as the previous approach wherein we have helper function. Step 3. If the prefix exists in dictionary and the remaining part of the string can be segmented, store the result in the memo table and return true. So here also same thing. If the prefix exists in the dictionary and the remaining part of the string can be segmented, then only we return true, okay? But before returning, we will be storing the result in the memo table. This memo table is nothing but our hash map or dictionary, okay? So in Python, we use the dictionary as hash map. And the table here we are referring is nothing but our dictionary, okay? And in step 4, if no valid segmentation is found, store false in the memo and return it. So basically, before we return something, we store it. That's the idea. So if you see here, the code is almost same, but we just use this dictionary, okay, as an additional layer. This is a storage for this, okay. So here we convert the word dict into set as previous approach. So that's what we're doing. And next we define our dictionary here, which is memo, okay. And next we define helper function with memoization. So you see that the function definition is almost same. So here we have some minor changes, but it's very self-explanatory. So here this is the same base case we have, okay. And next is we check the memo table. This is what something different from the previous approach. So here we're going to compute for the current recursion, right? So before we compute, we just check if the index is in memo. That means that if index is already computed and stored in memo, in that case we return the memo of index. That means we are returning the store result, okay. So if this is not the case, we're gonna compute it. So that's what this step about. So here this is same as a previous approach, right? So here also we're returning true, but before we returning true, we store that in our hash map at that particular index and return it, okay. So that's the idea, guys. And here also before returning false, we store that in the memo and we return false, okay. So similarly here also we call the helper from 0th index, okay. So that's how we written helper of 0. So let's look into complexes. The time complex of n square, where n is the length of the string s. So basically here we treat over all possible substrings, right? But how many number of substrings we have? So if you look into here, so this word geeks for geek space, you can also Google it. So here the total number of substrings of all lengths from 1 to n is what? N into n plus 1 by 2. So if we take this formula, we have n into n plus 1 by 2 substrings. And we're listing all this for once. So this n square by 2 plus n by 2. And effectively this is very small in front of n square by 2, so it is n square by 2, but this half factor is also very small when compared to n square, so it's n square. So effectively it's n square. Space complex is often for the recursion stack and memoization table. So basically in the previous approach as well we discussed the space complexity required for the recursion stack is often, and for the memoization table also here we require the space, right? So that's why it is also n, it is also n, so it is effectively 2n, but this 2 is very negligible in front of n, so it is n, okay. So if you still didn't get this, why I told n for the memoization table, because we stored the indices in the memo table, right? Memo table is nothing but the dictionary or hash map here, okay. So how many such indices we have? It is equal to the length of the string. So if we have a string of length 9, we have 9 indices. So that's why we require the space for 9 indices. So it is totally saying that we require n indices space. So it is O of n for this memoization. And the recursion stack as well, O of n, we discussed in the previous approach. So it's totally O of 2n, okay. Effectively reduced to O of n, okay. So as we discussed before, now I will be showing you how to convert this recursive function into the memoized version with just one line change. So guess what? We just need to add one annotation at rate of cache. Let me just submit this. See, this accepts solution and widths 22.5% of users. So basically how this got accepted. When we get a call for a particular index, we compute that and we store in the cache. Next time, if we get this call to the same particular index, then it would be written from the cache instead of computing it. So that's what our at rate of cache annotation is doing here, okay? So this is just like same as doing of hash map, but in some interviews, this won't be accepted because it depends on interview, right? So they would want you to implement a hash map based approach. That's why we had to learn that approach, okay? So I got the code ready for the hash map based approach. Let me try running this. So this accepts solution for the 3 cases. Let me try submitting this. So we see that this acts solution for all the test cases we have. Cool, right? So let's look into approach 3, which is bottom-up dynamic programming approach. So here the time complexity remains same, but the space complex should be optimized too often. That is because we won't be having that extra space for the recursion stack. We will be using the iteration here, that's why. So what is intuition? In the bottom-up approach, we use a DB array to store whether each prefix of the string can be segmented. For each index, we check if any substring any other index can form a valid word. So that's the idea, guys. So basically here we would be using the DP array instead of the hash map or the dictionary we used in previous approach, and then each index in DP array would be having the value boolean, that is like true or false, and true indicates that substring ending at that particular index can form a valid word. How can we say it form a valid word? So basically if we take a substring and it exists in the word dict, then it forms a valid word. So that's the idea, guys. So let me just consider the substring here. So if we consider the substring in the LeetCode from 4 to 8, so here the included indexes are from 4 to 7 because this excluded, right, this index. So that's why we get only till 7 and we get the word code. This code is there in the word dict. So and next what we need to check to mark this particular DP of 8 is equals to true. So for DP of 8 is equals to true, we should check that the previous substring also should be matching. So for that previous substring, what is the previous substring we have? So if we take that, we should check for DP of 4. This DP of 4 stores what? If the substring ending till index 3 of the string is a valid substring or not. So here DP of 4 is also true because this lead exists in the word dict, right? So that's the idea, guys. Don't worry if you don't get this. I will give a dry run of this approach. I just explained the high level thing here, but it would be very clear for you once I explain the dry run here, okay? So let's look into the algorithm. So basically what we do, firstly we have to create a DP array of size length of s plus 1 instance to false. So why we require that extra 1? Basically we have to store for each prefix, right? But we discussed initially, right, this empty string can also prefix. So to cover that empty prefix we use plus 1 length. So that 1 length will be used for this empty prefix, and each empty prefix is a valid word, right? That's the idea, guys. So for that reason we kept it to length of s plus 1 and all instances to false, and we said dp of 0 is equal to 2 to represent the empty prefix, because empty prefix is always a valid word, right? Because it's a substring of every word. Okay, so that's why we mark dp of 0 is equal to true, and always remember this is a base case. Okay, so basically in tabulation we form our solution based on the base cases. So we just look up our base cases and form the solutions iterated. That's the idea. Okay, in step 2, iterate to the string and check each substring. So basically we are clear about only empty prefix, and for all other prefixes or substrings we have to see if it exists in a word, and then only we have to mark that particular index true or false, right? So that's the second step. Step 3, if a substring exists in the dictionary and the previous part can be segmented, set dp of 5 equals to true. So basically what this means is, if the substring exists in the dictionary, that means let's say we take the code. So here code exists in the dictionary. So for filling that particular dp index, so here if we're considering a substring, means like it ranges from j to I, right? J is what the lower index and I is the higher index. So to set dp of I is equals to true, we have to consider if the previous string of this particular substring is also a valid word, and only we can fill dp of I is equals to true, because we are filling out the prefixes, right? It's not just the substring, we are filling out the prefixes. Prefix is what it can be empty prefix, or it can start at 0th index and end at any of the indexes. So to confidently say that the particular prefix ending at this index 7 is a valid word, then we have to check if the previous word is also a valid prefix. So that's why we have to check dp of j is equal to true. dp of j word, so the prefix ending till this point is valid word or not. So if that is a valid word, we can definitely say that this whole word ending at dp of I is a valid word. That's the idea, guys. This is the key. Okay, so don't worry, I'll show you a dry run. It would give a clear idea of what it is. Okay, step 4, return dp of length of as the final result. So basically each index in the dp array shows what any substring ending at that particular index can form a valid word. So if we can consider the last index, then it would store the whole string is a valid word or not, right? So that is, if we consider dp of 8, it would store what? It would store this whole prefix, which is LeetCode, is a valid word or not. So if it is a valid word, it could have been split as place separated words as a word dict. So that's the idea, guys. We just need to look at this last index in the dp array to say if the whole word is a valid or not. So let's look at the dry run, which would give you more idea. So basically we initialize all indices in the dp array to false. And what is the length of the dp array? Is just the length of the string plus 1. So here the length is what? It is 9. Okay. So here in the first step we mark dp of 0 is equal to true. This is for what case? This is the empty prefix case, because empty prefix is a valid word, right? That's why we put dp of 0 is equal to true, and later on we have to check. So basically and next we consider the prefix l. Okay, so this is the maximum prefix we can consider at this point. For this prefix we check if there is a word dict. Okay, it is not then a word dict, right? We have only lead encode, so that's why we mark it as false. I mean, we don't need to update it. So here we don't update it. Okay, so here update section says no match. In the iteration 3, what we do, we check for LE. Same here also we don't have it in a word dict, and similarly we do check for LE in the 4th iteration. And next in the 5th iteration we have lead. This word is there in the word dict, right? So now we have to set dp of 4 is equal to true. This is because we considered s of j till I, which is lead, and previously also we considered what? The empty prefix for this one, right? So before the lead only empty prefix is there. Both are true, hence we can say that dp of 4 is true. Okay, so one thing as here I'm considering the maximum possible prefix. Okay, so actually if you see in the code we will be considering every possible prefix, but here we are considering only maximum possible prefix in our dry run. It's not practical to show all in dry run, right? So that would be taking a lot of time, so it is not required as well. Okay, similarly in iteration 6 we check for word lead C. This is no match, and then in iteration 7 we check for lead co. So basically here you don't have match in the word dict. And next we check for this lead code COD. This is also no match. Next is a 9th iteration. So here we would be having the word lead code. So here this is the prefix we have. Okay, this is the maximum prefix out of which I told, right, like we can consider the part of it as well. So I'm considering CODE only. So we in CODE we have this word in verdict. We can mark DP of 8 is equal to true, but only if the previous substring is a valid word, right? So how can we check that if it's a valid word or not? We just need to check if DP of 4 is true, and DP of 4 is already true, right? Because we have lead, which is a valid word. So that's why we can mark DP of 8 is equal to true. Okay, so that's the idea, guys. So you got the idea, right? So basically, to mark a particular prefix as a valid word, you have to check that particular substring and the word which is just before that. If both are valid words, then we can mark that particular index in the DP as true. So let's look into the code, which is very simple. So firstly, we just insert a DP array. So this is the shortcut if you don't know. So basically here, we replicate the false for length of s plus 1 times. It would form a list of this length with all cells initialized to false. And next we are initializing DP of 0 is equal to 2. This is for the empty string case. And next this is the same case, right? We are just converting the verdict list into a set. This is for the faster lookups. And next is filling the DP array itself. So here we are considering the range from 1 to length of s plus 1. So you already know, right? This is x2 range and we will be getting the indices only from 1 to length of s. So if we consider this LeetCode, we will be getting the indices from 1 to length of s, which is 8. Okay, that way we're not exceeding the maximum possible index. So we won't be getting that index out of bound exceptions. So basically the substrings can range from 0 to I minus 1, right? So that's the idea, guys. So here that's why we're using the inner loop. And next we check if the substring is in the dictionary. So for that case we're checking s of j till lies in the word set. So this is the same case we discussed here, right? So here we check if s of 4 to 8 is in the verdict. So here the code is in the verdict, then it's a valid word. Before that we also need to check if DP of j is equal to true, because for this code alone cannot say if this prefix is a valid prefix or not, right? So that's why we have to check the previous as well. So for this we have to check till DP of 4. Okay, so that's what we're doing. So we'll be checking till DP of j. If this is also true, then we can mark DP of I is equal to true. Okay, so basically we fill this true once, and next onwards we don't need to care about the syntax, right? Because we have one valid prefix ending at that index. So that's why we have to break out of that loop. Okay, next is our step 4. We just need to return the result for the full string. That we can achieve by returning DP of length of s. So we just discussed here, right? That's the same thing here. So what are complexes here? The time complex is O of n square, where n is the length of the string. So this is same as the previous approach as we discussed. And the space complex is O of n. So basically here we're forming a DP array of length n plus 1, but 1 is very negligible in front of n. So that's why it is n only. So the space complex is O of n effectively. I got the code ready here. Let me try running this. This is the accept solution for the 3 cases. Let me try summon this. So this accept solution for the other test cases. Cool, right? And that's a wrap on solving the word break problem using 3 different approaches. If you found this breakdown useful, drop a comment below and share your thoughts. Don't forget to like the video, spread the word to your fellow coders, and hit the subscribe button for more in-depth coding tutorials. Also, do follow on Instagram for the latest updates. And if you're looking for resources or have some doubts and want to discuss, join our Telegram community. See you in the next one.